The universe is an enormous system of matter and energy, a system of masses in movement. Some masses, like stars, produce energy. Some, like planets, absorb energy, radiant energy from stars. Radiant energy from our sun reaches all the planets of the solar system, including, of course, the Earth. For our planet is part of a vast matter-energy system, as is everything on our planet. Part of our planet is matter, and part of it is energy. For instance, this rock is matter. What happens when the rock is put into this full beaker of water? What does this show us? Matter takes up space. Matter also has mass. When we measure the gravitational effect of the Earth on the rock's mass, we measure its weight. Will the rock move unless it's acted upon? No. We say it has inertia. Our planet, like our universe, is made up of matter, having mass and inertia, and taking up space. The state of matter can be solid, like these rocks, liquid, like this water, or gas, like the air. The different states can be explained on the basis of the kinetic molecular theory. Molecules in a solid are close together. This explains why solids have particular shapes. Liquids take the shape of their container. This happens because in liquids, the molecules are farther apart than they are in solids. In a gas, molecules are still farther apart. So gases tend to spread throughout whatever space they are in. The gas here is nitrogen dioxide. The smallest part of nitrogen dioxide is a molecule. A molecule of nitrogen dioxide is made up of 3 atoms, 1 of nitrogen and 2 of oxygen. When more than one kind of atom forms a molecule, the substance, like nitrogen dioxide, is a compound. Copper, which is composed of only one kind of atom, is an element. Scientists have found more than 100 different elements. We can think of an atom as composed of a nucleus with a positive charge, surrounded by electrons with negative charges. Nearly all the mass of the atom is concentrated in the nucleus. It is made up of protons, neutrons, and other particles. The number of protons and neutrons in the nucleus determines what kind of atom it is. These particles have been studied by modern nuclear physicists using particle accelerators. Protons and neutrons can be changed to other types of matter by causing them to collide with other particles at tremendous energy. The paths of the new particles can be observed with photographs made in a bubble chamber. The paths show that most of these particles exist only momentarily. From photographs, physicists have learned more about the structure of matter. They've also learned of antimatter with positive electrons and negative nuclei. So from a nucleus and orbiting electrons, from atoms joined together into molecules, comes all the matter of our planet and our universe. Living things and non-living things. The study of matter in motion led to our modern concepts of energy. The energy of motion is called kinetic energy. Kinetic energy can be transferred. This may happen when one object collides with another. Let's see what happens with 2 equal masses like these 2 balls. Ball number 1 will have the greater velocity. The ball it hits rolls farthest. The greater the velocity, the greater the kinetic energy transferred. Let's see what happens with two unequal masses, like these two balls. They will have about the same velocity, but the metal ball has the greater mass. The ball it hits rolls farthest. The greater the mass, the greater the kinetic energy transferred. The examples of kinetic energy we've seen with the rolling balls are related to potential energy. When we raised a ball, we gave it a certain potential, or possibility for movement. When the ball was released, the potential energy was converted to kinetic energy. Changes in kinetic energy are also responsible for change of state. Think of matter in the solid state, ice for example. Think of the molecules that make up ice. Although molecules of a solid are in constant motion, they maintain their same general positions. But as the solid is heated, the kinetic energy of the molecules increases. They begin moving farther apart. Matter changes from the solid state to the liquid state. Ice turns to water. As the molecules continue to gain in kinetic energy, they break apart from each other. Liquid changes to gas. Now the molecules spread out, filling the space they are in. Scientists studying gases at high energy, like those in the atmospheres of stars, observed a fourth state of matter, plasma. Matter in the sun's corona is a plasma. The atoms have been stripped of their electrons. Plasma conducts electricity and responds to magnetic fields. Most of the matter in the universe is plasma. The northern lights are caused by a bombardment of the Earth's atmosphere by a plasma. The plasma is the stream of electrified particles given off by the sun, which is called the solar wind. So the different states of matter can be explained on the basis of atoms and molecules in movement. But within every atom, electrons are moving in orbits. Each orbit is a result of a certain energy level of the electrons. In metals, like the copper wire in this circuit, some of these orbiting electrons can move from atom to atom. The kinetic energy of electrons in movement we call electric energy. Electrons in the atoms that make up this metal filament absorb energy from the electric current. These electrons move into higher energy levels. Almost immediately, they fall back to their original energy levels and give off their extra energy as a photon of light. This results in the steady light we see. Electrons produce light in fluorescent tubes in a similar way. Visible light waves are only part of the wide spectrum of energy we call the electromagnetic spectrum. These radiations range from the low energies of radio to the high energies of X-rays and gamma rays. So we see that electrons in motion are responsible for many forms of energy, and that matter and energy are closely related. Electrons also are involved in chemical changes. Atoms combine or separate, either using or giving off energy, as when sulfuric acid reacts with sugar. In this chemical reaction, magnesium is burning in open air. But in a flash bulb, the magnesium is enclosed, and this flash bulb is in balance with an identical bulb. Let's electrically ignite the magnesium in one of the bulbs. The bulbs are still balanced. The light and heat energy produced are a result of a conversion of chemical energy in the magnesium and oxygen atoms. But as far as we can measure with this balance, no matter is lost when the magnesium burns. Experiments like this one suggest that matter and energy are never created or destroyed. But the behavior of radioactive materials provides evidence for a different relationship between matter and energy. Every flash on this instrument means that somewhere in the material being examined, a particle has emerged from the nucleus of an atom. Nuclear decay is taking place in this radioactive rock. Now we're watching nuclear decay in a cloud chamber. Scientists know that particles resulting from this decay have less mass than the original particles, but energy appears in place of the lost mass. In atoms of radioactive materials, the same loss of mass takes place. Matter is converted to energy. In a nuclear reactor, this conversion of matter to energy occurs at a more rapid rate. Nuclear fission takes place. A different sort of conversion happens in the sun and other stars. The nuclei of atoms combine or fuse together. In nuclear fusion, matter is also lost and tremendous amounts of energy produced. The fact that matter can be converted to energy helps illustrate the law of conservation of matter and energy. The law means that in nuclear reactions, as well as in physical changes and chemical changes, matter may be lost, but in its place, an equivalent amount of energy always appears. This knowledge has led to the modern concept of the universe as a great matter-energy system in which the total amount of matter and energy is always the same. This concept of the conservation of matter and energy has become the basis of modern science.